Great to be here. I'm going to tell you about the planet formation, and consequence of planet formation for free floating planets. One thing I want to add to all previous talks is that planets, first you have to form them, and then you have to and then you have to eject them. So if there is a free floating planet, a piece of rock in the space that is as massive as, and has the size or mass of a planet, it has formed somewhere and got ejected out. Ejection does not mean put a limit at 100 AU, 5,000 AU and say it is passed over that. We do that to prevent extra calculations. When I want to calculate, I'm going to show you here formation of terrestrial planets. When I want to calculate terrestrial planets, when I want to form terrestrial planets at 1 AU, if an object goes at 20 AU, is no longer relevant to my calculations. I drop that so I don't waste calculation computational time. That doesn't mean it was ejected. The system, the planet is ejected when it gets out of the potential well of sun and gets away. All those interstellar objects, they got ejected. They came out of the potential well of the central star and they passed by sun. There is a criteria for that. And sorry, there's a criterion for that. And I'm going to mention that criterion. And then I want to show you how applying that criterion to formation results into planet population or the statistic of planet free floating planets. It is very important to keep in mind that these planets have to form somewhere. The other thing I want to mention that planet-planet interaction happens during the formation. When a system is formed, it is clean. It has done all the nonsense and all the crap that it wants to do. So saying that I put a planet in there and see how it ejects, it violates the physics of planet formation. This is very, very important. You can't just by hand put things in there and see how it behaves. It does what the physics of planet formation says. So let's see how that physics applies and what it gives us as far as the final product and formation and the formation of free floating planets. Okay, so why am I talking about terrestrial planets? Well, many of you may know that, I've been working on planet binaries for 30 years. And along to that, I've been also trying to figure out how to form our terrestrial planets, Earth and Venus and Mars, how to bring water to them and everything. So during the past 5-6 years, we had the luxury of having access to a lot of computers. So we decided instead of coming up with ideas, we decided that to start from scratch, put everything in the computer, run a ton of simulations, literally about 2,000 simulations. I'm going to show you the result of 1,100 of them. And then let the physics of formation tell us what happens. So the only assumption that I make here are very simple things like what happens when objects collide with one another. But whatever you see has no pre-assumption in the foundation. We just put the objects in there and say, go. And we run it for 2,000 different times. And we see what comes out of it. Okay. What I'm going to talk about is the stage of giant impact. Many of you have seen this. I'm going to start running that, but before that. So what we have here is a bunch of planetary embryos sitting next to each other. Sun is over there. I'm doing it in the context of our solar system. You can do it for whatever planetary system you want. I put Jupiter at 5.2. Saturn is at 9.8, 9.7. And a bunch of planetary embryos. These are moon to Mars sized bodies. And a population about 2,000-3,000 of planetesimals. These are small objects. And you need them to make sure that these planetary embryos, when they interact with one another, the eccentricity stays low. Forget about the color. This is part of another simulation for water delivery, and I don't care about that. Resonances are with mean motion resonances with Jupiter. I have indicated that. I'm going to start this and see where it takes us. At the same point, I'm going to stop it and explain things. Okay, this is good. As you see that mean motion resonances increase the eccentricity of the objects, both embryos and planetesimals. But there is another thing here, this thing that doesn't correspond to any of those lines. This is the effect of secular resonance of Saturn. This is the new 6 for the celestial mechanics among us. This is very important. When Saturn, whatever it is, it starts its secular resonance at about 2.1 AU, and as the secular resonance ejects material from the disk, it moves inward to about 1.9, and then it stops there. Why is this important? Because anything that is inside of this is trapped, and it has no place to go. And they start hitting each other, breaking each other into pieces, and attaching to each other, and growing and growing and growing, and form terrestrial planets. So one thing I want you to take from this, if that new 6 didn't exist, the situation would have been very, very different. If the mid-motion resonances didn't exist, if Jupiter didn't exist, we wouldn't have asteroid belt. So these are important things. I will get back to them. But the most important thing here for now is that there is this new 6. The new 6 confined everything inside of it. There's also the secular resonance of Jupiter sitting at 0.9 AU. You see a little bit of it, but that is unimportant. And terrestrial planet formation happens. Let's see if I can continue this, and then let's go to here, for instance, and stop it. So this is the final product. The most important thing to consider here is that these simulations are stochastic, and they're not meant to produce the solar system. You run 2,000 of them, and you get 2,000 different results. We don't run these to say, oh, this is the initial condition that became our solar system. We run this to figure out the underlying physics that goes into terrestrial planet formation. And here, for instance, what results into scattering or ejection of the objects. I deliberately chose that doesn't give you solar system and puts a big planet in the asteroid belt to remind myself to tell you that when you see these simulations, keep in mind these are stochastic, and the purpose of it is to reveal the underlying physics, proof of concept, not to actually reproduce our solar system. So now, we have, like I said, we have done these simulations for a very for a large number of the systems. Here I'm showing 6 different types of it. First of all, for different distribution of material, R to power negative something is the initial distribution of solid material, protoplanetary disk, and planetesimals. It represents its surface density, the surface density of the disk. This means that the surface density, initially the surface density of the disk was proportional to R to negative 0.5, R to negative 1, and so on. Here, there are Jupiter and Saturn for different simulations. Here, there are no giant planets. As you see, when there are no giant planets, there is no peaks. As you see, when there are no giant planets, even when the planetary embryos interact with each other, even when you assume that when they hit each other, they stick to each other and grow through perfect merging. If there is no giant planet sitting out there, you don't see an increase in eccentricity. If there is no increase in eccentricity, as Sean showed that the planet doesn't go away, become a far planet or gets ejected. I must apologize. My heart is racing because I'm 11 hours jet lag. So if my mouth goes dry, if I talk fast, please, I sincerely apologize for that. And I forget words. So you need those giant planets to do what we want to do. That's the most important thing that you take from planet formation. That's one thing. The second thing is that these planets have to form. So let's form them and see what comes out of it. So we are in the process of running 2,000 simulations similar to what I showed, and I'm going to show here the result of 1,100 of them. Each one of these is one simulation by itself. At the end, in the last slide, I'll explain what one simulation has for the origin of free-floating planets. But to get to that, I'm going to show you a statistic of all these 1,100 simulations. Within these 1,100 simulations, we have 70,000 big objects. These are the big objects. So we have 70,000 of these big objects. I'm going to put them all together, but I want you to keep in mind, what I'm going to show you is not one simulations of 70,000. Is the result of 1,100 individual simulations. That's very important. So Keep that in mind. I keep repeating this so we have that as our perspective as we go through. So if you're interested in the details of the simulations, they're out there. The ejection criterion is that the total mechanical energy must become positive. Remember from your high school physics that when an object gets trapped into a potential well, the total mechanical energy becomes negative. That total mechanical energy must become positive. And in order to do that, the eccentricity must become either 1 or larger than 1. When you have eccentricity of 1, then your object is moving on a straight line. It is no longer bound to the initial center. It keeps going. If it is larger than 1, then the orbit is different, hyperbolic or parabolic, and keeps going away. Okay, so that is our criteria. But there is one big caveat on that. I told you I'm jet lagged. So there's one big caveat on that. You know, when you run these simulations, you say to the code that every certain number of years, give me output. You can say, give me output every second, right? And then you run it for 200 million years. You better have access to huge amount of data, space to actually save this data. It is impractical. So what do? We normally decide how many years we need, and then we say to the code, give us that. For these simulations I'm going to show you, we decided that every 1,000 years, we're going to ask for an output. Okay, so every 1,000 years, I'm asking for an output, and one planet is here and has eccentricity of 0.999. And then 1,000 years before stop on integration, it has eccentricity 0.999. And the integration stops right there. It is quite possible that instead of 200 million years, if I had run that simulation for 200 million and 1,000, extra 1,000 years, the eccentricity of that object would be 1, and it would go out of the system. So somehow I have to relax this, but not much. So I'm going to relax it by saying that I consider eccentricity 0.9 to 1, but when I show you the results, I draw your attention to eccentricity of 1, and then you see what comes out of that. But keep in mind that not all 0.9 eccentricities are ejected. We have Oort cloud objects, comets on 0.0999, and not all, and some of the 0.9 eccentricities, if the simulations were run longer, would have been ejected. So keep that in mind. And at the end, I put them all in context. So these are the end point of all those 76,000 large bodies and for 1,100 simulations. What I'm showing here, the final eccentricity, and what I'm showing here is the initial semi-major axis. That is where they were. That's the disk. And that's where the planetary embryos were. And then we ran for 200 million years, and we ran for as long as the integration was required to run for that specific object. And then the integration stopped. So this is at the end of the integration, not necessarily 200 million years, whatever it took for that object for its integration to stop. This is not one integration, that's 1,100 integration. There are some properties to that, but before that, if you want to see what stayed after 200 million years for all these 1,100, that's what it stayed. That is 1,100 simulations, and at the end, at the end of 200 million integration, this is what it stayed. So a lot of these objects up here, they were no longer part of the end model, end system. Some of them got ejected, large majority of them collided with each other and got absorbed into the final planet. So what you see here is not necessarily ejection. It means that, for instance, that one up there might have collided with another one, and then integration stopped for it. This is the final product, okay? But let's go back again to here and see what we can learn from this. There's a structure to it. First, these are the mean motion resonances with Jupiter. This is where the circular resonance of Saturn is. And remember, this is your distance. That's circular resonance of Saturn is. This is compared to what stays at the end. This is the region where the planet formation happens. These are your planets. These are not necessarily all of them, but these are the embryos that went into the formation of the final planets. We want to consider these. Remember that criteria, 0.9 to 1? These are the 0.9 to 1 ones, all right? Not all of them get ejected, but let's see what happens to them. There is one other source of ejection or scattering here. If you can, I give you 5 seconds to look at it. If you spot that, I buy you a beer. I make this bet. I have made this bet many places for different things, and people know I'm good. I'm good for it. So surely I will buy you a beer. It's up there. So you see those little things? You see that stuff here? That's the one. That's this one. They immediately got ejected, or they immediately got absorbed, and they no longer existed, right? And those are the ones that are not related to any resonance. Those are the ones that are very, very close to Jupiter. So being affected by Jupiter, either they got scattered, they collided with other bodies, or they got ejected. So let's look at those for now, and then I carry you through this part. So let's look at those for now. What I'm showing here is that, so for 4 to 4.5, what I'm showing in the initial semi-major axis, this is that little thing, I magnified it, and this is their mass. Okay, so the masses seem to be, this is the initial mass. The initially, whatever we put over there, seem to be around 0.3 to 3 Mars mass. Now, let's see what happens when I put the final mass in there. Okay, go back. So, final mass. Except for a few, except for like this one here, that one here, that one here. The final mass and initial mass is the same. They sit on top of each other, which means those objects got immediately out of the system, either scattered out, scattered farther away, collided with other bodies, or actually got scattered out of the system, right? So let's see if they get scattered out of the system. Let's look at their eccentricity and see what is the mass that associates with that eccentricity. So yes, large majority of them, what you see here is the lifetime. Large majority of them, they got scattered within the first 100,000 years. And what you see here is the final eccentricity. We want to focus on this region and the initial semi-major axis. These are the objects that we want to focus on. This line here simply means that the eccentricity of these objects reached the large value in a very short time, within the first 10 years, 100 years, before the first output was written out. So in our case, before the first 1,000 years, they got scattered out or they got ejected. So that is not the representative of any physics. This is just code. Okay. So this is stuff what we want to work with. Let's see what is their mass. This is their final mass and the final eccentricity. We want to work with this stuff up there, 0.9 to 1. And as you see, the mass of these objects is around 0.3 to 3 Mars mass, maybe 5 Mars mass. So you're talking about scattering, but not very many. Remember, this was outcome of This was out of 70,000 objects, outcome of 1,100 simulations. We can actually count how many objects get ejected, right? So keep that in mind. You run all the simulations, only a handful comes out and gets out of the potential well. Now, let's go back to this area and do the same thing for that. The lifetime in terms of eccentricity, and this is for this area. This is the area of 0.89 to 1. Let me go back here quickly. Okay. Yes. Sorry, pushing wrong button. So 0.9 to 1. This whole thing. I'm going to magnify this whole thing. So that's what it is. 0.9 to 1. As you see, the lifetime shows that all of them, they get out within the first 100 million years. Large majority of them within the first 5, 6, before the first 10 million years, they get out. So they are unstable, okay? But that doesn't mean they were ejected. So now I'm showing their final mass for the, so again, this is the eccentricity, that range of eccentricity we are interested in, and I'm showing their final mass. The ones that definitely get ejected are up there, only a few out of 70,000. But if you want to consider, if you relax your criterion and you want to consider the whole thing, again, you're talking about the mass of about 0.3 to about 1 to 3 point mass. And this shows the same thing again, the mass for the, so to the last two slides for statistic analysis. Number of objects with eccentricities that between 0.9 and 1. Out of 70,000, only 8 of them got actually out of the potential well, right? 8 to, let's say 2. So about 0.1%. Even if you consider this 0.99 as ejection, you're talking about 0.1%. 0.1% probability for a terrestrial planet formation to give you a free-floating planet. That's what it means. So, right, that's what it means, 0.1% to give you, right? And the mass of them, that 0.1% will give you something between about 0.2 Mars mass to less than 1 Mars mass. Let's say 1 Mars mass. The simulation showed about 3 Mars mass, but when you actually go through single simulations and count them, you're talking about, let's say 0.4 to, I show you the next slide, 0.4 to about 1, probably 1.5 Mars mass. So that probability of 0.1 for that type of mass. What I'm showing here is actual simulations. These are individual simulations, right? Up until this, I was showing you the result of 1,100 simulations. Now I'm showing you the result of single simulations. If there is no giant planet, there is no scattering, there is no free-floating planet. If the giant planets are in circular orbit, the same thing. You need giant planets, and you need giant planets to interact with the planet formation region, with the terrestrial planet formation region. If you take Jupiter and its current orbit, and if you take Jupiter and Saturn in their current orbit, these two represent two different sets, and these two represent two different sets. You see, when there is only Jupiter, the percentage for objects to have eccentricity larger than 0.9 is only 1 to 3%. The mass is within the range of 0.5 mass. When you add Saturn, that new 6 comes up. That new 6 does its job. When you add Saturn in their current orbit, then the percentage for 0.9 eccentricity and higher goes up, and the mass gets close to about 0.1. So Saturn plays important role in ejecting material or planets out of the potential well of sun. If you take Jupiter and make it eccentric, or you take Jupiter and Saturn and make it eccentric, then the percentage goes high as well, and the mass goes higher as well. Now, eccentric Jupiter and Saturn we don't have in our solar system, but in extrasolar planets, you can do same thing for extrasolar planets as well. So, this is my last slide. In order to eject something out of the potential well of sun, you need big objects. You need big objects so they can actually push the thing up. And the terrestrial planet formation is a low yield process that in producing free floating planets. So if you, the most plausible mechanism for having terrestrial class or super Earth free floating planets, if you discover them, is not the formation of terrestrial of that object, it's the formation of giant planets. When there are giant planets, as they are forming, when the core is 2, 3, 4, 5, 6, 10 Earth mass, while it is forming, it goes through two things. Either it continues forming and forms gas giant for you, or most likely it moves through the interaction with the disk and migrates. That migration has two consequences. Some of the time, the cores interact with one another, throw each other out. Then, so if you find something like 3, 4, 5 Earth mass planet literally roaming the space, that object most likely was scattered during giant planet formation. And in most of the time, in the competition between formation and migration wins by a huge amount. And if you are interested, I would be happy to bring you to my office, sit over there, I give you the code, we go through it, and you will see migration wins by a huge amount. Okay, thank you so much.
It's not a, I'm sorry.
It's almost no time, but a very quick one from Shude.
So my plans is usually for M dwarfs, right? And those probably form giant Jupiters less efficiently. Are you saying that ejection will be less efficient?
In around M dwarfs? Oh, no, not at all. No. Yeah. So if anything is even more, your potential well is not as deep as Sun. Yeah. No. No.
But you are saying you need the giant Jupiters to do this.
Now I see what you're saying. Okay. That was a very, very good question. So please allow me to answer this. Yeah. So here's the thing. Migration wins over formation. And the biggest consequence of migration winning over formation is that the final planets becoming giant planet has a lower chance, and the higher chance is for the forming giant planet migrate through, right? So if we don't see them, it doesn't mean that the formation is inefficient. It means that the migration is much more efficient. A prime example of that on those early RV velocities, GJ876, 2.6 and 3.2 giant planets, and the Uranus mass planets sitting at 30 days, 60 days, 120 days orbit. And 47 UMA has, they're all around M stars. GJ581, these has a Saturn mass and a Jupiter mass. So the rarity is the competition between formation and migration. However, I'm a huge fan of M stars having giant planets.